Welcome back to the third season of our Lighthouse project, exploring sustainable AI. Artificial intelligence is at the heart of the digital revolution, driving advancements in technology, healthcare, finance, and beyond. From the algorithms that power our search engines to the neural networks that diagnose diseases, AI is transforming every aspect of our lives. But as we marvel at these advancements, there's an underlying cost that we cannot ignore: the substantial energy required to fuel these intelligent systems. Training AI models, particularly deep learning networks, demands vast computational resources. The energy consumed in training these models is staggering. Consider this: training a single large AI model can consume as much electricity as an entire household does over several years. This energy use translates directly into carbon emissions, contributing to the global challenge of climate change. For example, training a state-of-the-art neural network like the GPT-3, which boasts 175 billion parameters, is estimated to have a carbon footprint equivalent to driving a car for several 100,000 miles. As these models grow in size and complexity, their environmental impact becomes a pressing concern. The carbon footprint of AI is not just a technical issue, it's an ethical one. Every computation, every model iteration consumes energy, often derived from fossil fuels. This raises a critical question: how do we continue to push the boundaries of AI innovation while minimizing its environmental impact? In the past, the focus of AI research was almost exclusively on performance metrics like accuracy, speed, and efficiency. However, as the environmental implications of large-scale AI training become more apparent, there's a growing movement to also consider energy consumption and carbon emissions as key metrics of success. Reporting these alongside traditional performance measures is not just good practice. Is essential for the responsible development of AI. This shift in focus is part of a broader trend towards green AI, where the environmental cost of AI technologies is given as much importance as their technical performance. This movement is gaining traction, driven by the realization that sustainable AI is not just about doing good. It's about ensuring the long-term viability of the technology itself. In this video, we will explore the methods used to estimate and monitor the energy consumption and the carbon footprint of AI models. We'll delve into why these methods are crucial, how they are implemented, and what tools are available to help AI practitioners make informed, responsible decisions. Welcome to a journey towards a more sustainable future for AI. Let's dive in and uncover the energy costs behind the algorithms driving. To understand the energy demands of machine learning models, we turn to a key resource: the paper Estimation of Energy Consumption in Machine Learning by Eva Garcia-Martin and colleagues. This paper serves as a foundational guide, providing a comprehensive overview of how energy consumption can be estimated in machine learning applications. Firstly, let's discuss performance monitoring counters, or PMCs. These are specialized registers within modern processors, like those from Intel, that count specific hardware-related events, such as cache misses. PMCs are split into two categories: core and on-core. Core PMCs are associated with components like the arithmetic logic unit, registers, and caches within the processor core. On-core PMCs, on the other hand, are linked to components outside the core, such as DRAM and memory controllers. One of the paper's key contributions is its taxonomy of power estimation models, which are categorized into software level and hardware level. Each level offers a different perspective on how energy consumption can be estimated and optimized within machine learning applications. At the software level, models estimate the energy consumption of entire applications or specific algorithms. This includes understanding the energy cost of various operations within a neural network, such as the multiply-accumulate operation that dominate the computation in convolutional layers. At the instruction level, energy estimation models break down the energy usage by specific instructions, offering granular insights into which operation within a machine learning algorithm consume the most power. This approach is particularly useful for optimizing code to reduce energy consumption. At the hardware level, the focus shifts to specific components like CPUs, GPUs, and memory. By understanding which parts of the hardware are most energy intensive, researchers can design more efficient systems or choose the most appropriate hardware for their AI workloads. The paper further categorized the approaches to estimate energy consumption into four main techniques: performance counters, simulation, instruction level estimation, and real-time power estimation. Each technique offers unique advantages depending on the level of detail required and the computational resources available. Performance counters, which are registers in modern processors that count hardware-related events, are a popular method for estimating energy consumption. By combining these counters with regression techniques, researchers can estimate power usage during the training of deep learning models. This method is advantageous due to its low overhead and broad applicability across different platforms. Simulation-based approaches, while offering detailed insights into the energy consumption of various hardware components, can introduce significant computational overhead. These methods are highly accurate but are less practical for large-scale experiments. By utilizing these estimation techniques, researchers can gain a comprehensive understanding of the energy dynamics in their machine learning models. This knowledge is crucial for developing more energy-efficient AI systems and for making informed decisions about model design and deployment. Let's dive into some real-world use cases in this paper. Real-time power estimation and thread scheduling via performance counters. The authors present a model to estimate power consumption by correlating PMCs to observed power consumption. Based on platform constraints, they restrict the number of studied performance counters to 4. They have chosen these 4 performance counters as the ones with highest correlations to real measured power. They form the power model by assigning weights to PMCs. They do this by running micro-benchmarks and applying multiple linear regression to real power measured with the watts-per power meter. They have validated their model by testing it and comparing it to real power measurements on 3 different benchmarks. The main difference between this work and others is that they only use the performance counters that are available at runtime in a single run, allowing for real-time power estimation. And about the portable scalable per-core power estimation for intelligent resource management, the authors present a methodology to produce per-core power models in real time using PMCs and temperature sensor readings. As the previous models presented above, they first find the PMCs that correlate strongly with measured power. They sample those PMCs while running micro benchmarks and then apply linear regression to give a weight to each PMC. The best set of PMCs is unique for each system. Their methodology has the following steps. First, they identify the PMCs that represent the heavily used parts of a core's microarchitecture. They derive the following 4 categories: floating point units, memory, stalls, and instructions retired. The instructions retired refer to the number of instructions that were completely executed by the CPU. The stalls category measure resource stalls to understand how the out-of-order logic contributes to power usage, since if an instruction stalls, that can contribute to an increase of dynamic power. Second, they rank the PMCs by running a set of micro-benchmarks that cover the categories mentioned in the first step. In this paper, accurate and stable runtime power modeling for mobile and embedded CPUs, the authors built a runtime power model for ARM's Cortex-A7 and A15 for the purpose of runtime power management and design space exploration for the application. They perform a thorough investigation of PMC event selection using statistical techniques such as hierarchical clustering and R2 analysis to capture the relationship between power and the PMC data. They also measure collinearity of the PMCs with each other to avoid duplicating information that is used for building the power models. They use the optimal PMC events from the PMC event selection phase and use correlation correlation techniques to relate these events to the clock frequency and CPU voltage. They model the power at the cluster level, which includes multiple cores and their caches. They also build models for varying number of cores and different core affinities. Their benchmarks include 60 workloads created from different sources such as MyBench, LMBench, and others to exercise the CPU, memory, and the I/O. Energy estimation in machine learning is becoming increasingly crucial as AI systems continue to grow in complexity and scale. Estimating the energy consumption of machine learning models serves several purposes, from optimizing the efficiency of algorithms to reducing the environmental impact of AI technologies. Machine learning models, particularly deep neural networks, consist of two main computational phases: training and inference. During the training phase, the model learns by adjusting weights and biases across multiple layers, a process that is computationally intensive and typically performed on powerful hardware like GPUs and CPUs. The inference phase, where the model applies learned parameters to new data, often runs on less powerful devices such as smartphones and embedded systems. Research in this area has made significant strides, particularly in optimizing the energy efficiency of deep learning models. Early approaches to energy estimation in neural networks focused on counting operations like multiply, accumulate to estimate floating point operations. These were used as proxies for energy consumption, particularly for accessing memory, which is a major contributor to energy use. One of the early and effective strategies was reducing the number of weights and parameters in the model through techniques like pruning and compression. By minimizing the memory access required, these optimizations significantly lower energy consumption without compromising model accuracy. A more sophisticated approach to energy estimation models involves accounting for the energy costs at different levels of the memory hierarchy. For example, some models estimate how often data is reused across these levels from DRAM to registers and use this information to optimize energy consumption. This method has been particularly effective when mapping neural networks to specialized hardware architectures like Iris, designed for energy-efficient deep learning. Another key development in this field is the use of performance counter specialized registers that track hardware events like cache misses or memory accesses. Tools like Synergy and Neural Power apply regression techniques to correlate these events with power usage, enabling accurate energy estimation for both training and inference phases on general-purpose processors and GPUs. The majority of energy estimation research has traditionally focused on the inference phase, where the goal is to optimize pre-trained models for energy efficiency. However, there is a growing interest in applying these techniques during the training phase as well. Recent advancements are exploring the use of reinforcement learning, Bayesian optimization, and genetic algorithms to automate the design of energy-aware neural network models. As AI continues to expand into more resource-constrained environments, such as mobile and embedded systems, the need for accurate and efficient energy estimation models becomes even more critical. These advancements are not just about reducing costs, they are essential for developing sustainable AI that minimizes its environmental footprint. As we've seen throughout this video, the rapid advancement of AI comes with significant energy demands. Estimating and monitoring the energy consumption and carbon footprint of machine learning models isn't just a technical necessity, it's a moral imperative. To learn more about energy-efficient AI practices and the tools we've discussed, please join us for Lighthouse Project Season 3.